Alright, hello guys, welcome back to my stream. Welcome back to my channel. So tonight, we will be discussing about engineering materials for tomorrow's test. Is everyone okay? Are you guys ready? If you are ready, you can type in the chat box that you are ready. Okay, ready. Let's fucking go. Alright, guys. So tonight we'll be starting off with dislocation and strengthening mechanisms, and then we'll be moving on to phase transformation. Okay. So, Bismillahirrahmanirrahim. So dislocation and strengthening mechanism. So what's the main concept behind this? Diam. Housemate bising. Okay, so this is the basic concept behind dislocation. So dislocation is plastic deformation by plastic. Oh, I should show. Okay, so let's choose yellow. Okay, so motion of dislocation is plastic deformation by plastic shear or slip, where one plane of atoms slide over adjacent plane by defect motion. It means that if one plane has a different atom bonding with another plane, it would have a dislocation. So when stress is applied, that dislocation moves. So when that, what causes that movement is the shear stress. So if the atom's bond breaks, it is plastically deformed. But if it is elastically deformed, the bonds would just not move at all. So the more dislocations you have, the stronger a material can be, because the planes would slip harder, or it will be harder for a plane to slip from each other. Okay, so this we will talk about the characteristics of dislocation. So kat sini is one plane with one row of extra atom, and this is another plane with one less row of atom. So in the middle, we call this a dislocation point. So the above plane faces compression, the below plane faces tension. Okay, so this compression and tension creates strain fields. Okay, so strain fields, amount of dislocation effect. Okay, so this one you guys can read basically. So I'm just gonna go through the theory, because it would be boring to just read out the facts. So okay, let's go over here. So what happens in different types of materials for dislocation? In metals, there is easy motion, and because it has non-directional bonding, it means that the atomic bonding between the planes is not strong. So metals tend to become very ductile because they can deform easily. Ceramics, on the other hand, has a very hard motion, right? Because it is into two categories, which is covalent ceramics and ionic ceramics. Covalent ceramics have a directional bonding, such as carbon, silicon. Ionic bonding is like when you have positive, negative ionic compounds, which is natrium and chloride. Okay. Okay, so dislocation are generated during deformation. Heavy deformation means the dislocation is more in a certain volume. So it has higher density of dislocation if you deform it very hard, such as cold working. If you compress the compound really hard, the dislocation would compress with each other, so it has a higher density. Okay, so where does this dislocation exist, or how does this dislocation appears? So it appears in internal defects, surface irregularities, grain boundaries, and existing dislocation. Okay, so let's say you have a strain field. This is what we call a strain field. So this is compression and this is tension, like I mentioned. So what happens if you have the strain field similar to each other and position next to each other? So dislocation of the same sign on the slip plane exerts repulsive force, which means it pushes with one another. So if the system or the strain field is opposite, atas compression, bawah tension, next to tension and compression, so it will exert attractive force. Okay, so that is the basics of the strain fields. Okay, so now we're going into slip system. Okay, so you guys must hear Dr. Iswadi say a lot about slipping from last semester or last year. So slipping is the combination. Slipping is the deformation of the planes or the direction of the planes. You have a compound, and where does that compound deform, or how does it deform according to what factors? So it actually slips in a certain direction, which is based on the microstructure. So there is two types of slip system: slip direction and also slip plane. The slip direction is the direction of the movement of the deformation. Slip plane is the plane that allows the slippage. Okay, so we have different types of structures here: FCC and BCC. FCC is face centered. Apa kah C ni apa? B is base centered. Centroid. Okay, so this is the different shapes of the slip plane. Slip plane of FCC is like a triangle. Slip plane of BCC is like a rectangle, and the slip direction is also different. Okay, so slip in single crystals. What does it mean as single crystal? It means that the compound only has one slip plane. If you have multiple crystals in a compound, it will have multiple slip planes. Theoretically, theoretically we want to study the compound with a single crystal, but it's actually hard to find compounds with single crystal. Most of the metals are polycrystal. That's why we call metals as polycrystalline structure, because they have multiple crystals which has multiple slip planes. Okay. Okay, so this one you guys can read. Okay, so plastic deformation of polycrystalline materials. Like I said, when that compound has multiple crystals, it will have different planes, such as here. You can see here that they have lines. They have lines. So it would be hard for the compound to deform from one direction to another direction. So the more crystals you have, the harder it is to deform. Okay, so that will we will talk about that after this. So the slip motion. So stronger grain boundaries, pin deformations, which means that if you have a grain boundary like this, so at the middle of the grain boundary, where the grain boundary meets, is where it is hard to deform. Okay, so okay. So let's say we want to deform the material. How do we want to deform? Is by rolling. Rolling is like the process of compression. So there is before rolling and after rolling. So before rolling, the compound is isotropic, and the grains is randomly shaped. What it means as randomly shaped is like this. It is some of the grains are big and some of the grains are small. After rolling, the rolling affects grain orientation and shape. So after rolling, you will find a decrease in grain. Okay, so that the reducing the grain size is one way or one technique of strengthening a material. Okay, so this is where we need to focus on. So this is this first page is more on like the process of this dislocation, which I will not talk about much. You guys can read. This is the strengthening mechanisms that we want to focus tonight. Okay, for this topic. So there are four techniques of strengthening a material. First, we have grain size reduction. We have solid solution strengthening. We have precipitation hardening, and we also have strain hardening. Okay, so what is grain size reduction? Grain boundaries are barriers to slip. So the barrier strength increases with increasing angle of misorientation. So if you have more grains, there will be much more grain boundaries colliding with each other. So this is one of example of a grain boundary. If you have multiple grain boundaries, so it will be harder for the material to deform in a certain direction. So that is what makes the material stronger. So that is grain size reduction. What about solid solution strengthening? So it means that we introduce impure atoms to distort the lattice and generate stress. Okay, so this is what we call alloying. When you have a different we have a different metal, we combine with a different metal, because different metals have different atom size. So let's put here different atom sizes. So with different atom sizes, you can mix the different compounds, and then you can generate what we call impurities. So there are two types. If the atoms are smaller, it is called small impurities. If it's a big atom, it's a big impurity. Okay, so so far it's quite easy actually. Okay, now we go into precipitation hardening. So what does precipitation means? Precipitate means dia macam, kalau in Malay, precipitate tu dia macam larutan yang tak larut. Kalau kacau kopi, pasal ada serbuk dia lagi, so serbuk-serbuk tu nama dia precipitate. So how do we relate in the materials? So that little serbuks are what we call precipitates, and that precipitates this allows, or like makes the direction of the dislocation harder. Or in order for one plane to deform, you need to overcome the precipitates shear stress. Okay, so for example, hard precipitates are difficult to shear. For like if you have a plane, this is metal and this is also metal, and you have like a small SiC, silicon carbon in the middle. So silicon carbon is a atom where you need to overcome the shear stress of the atom in order for you to deform the plane. So this is before. So after shearing, it will look like this. One half of the silicon carbon is separated from the other half. Okay, so that is what we call precipitation hardening. So okay, let's read. Dislocation advances but precipitates as pinning sites with spacing. Pinning means a point where stress is concentrated, and you, in order to deform, you need to overcome that stress. So that is what pinning means. So this is the pinning of the shear stress. So if you have enough shear stress, the precipitate would separate into two. Okay. So this is strain hardening. So strain hardening is like we physically temper the not temper lah, like deform the material. Okay. So this is the four common forming operations. You have forging, drawing, rolling, and extrusion. Okay. So in our lab this semester, we learn about cold rolling, cold working because it's considered cold because we do it in a room temperature. So it's actually rolling, if you guys have done the experiment. So what happens? What actually happens in the structure of the material when we physically deform the material? It would change the dislocation density. So what does that mean? It means that the total dislocation length over unit volume is increased. So the higher the dislocation density, the higher the yield stress, the higher the tensile stress, and lower ductility. Okay. So if you want a harder material, if you want a stronger material, you need to increase the dislocation density. Okay. So is there any questions for the first chapter? Quite fast lah actually. How many minutes has it been? Oh, it's 20 minutes. Okay, so is everyone okay with dislocation and strengthening mechanisms? You guys can ask in the chat box. The formulas, you don't need to worry much lah, because there might not be any calculations in the test tomorrow. So yeah, this one just for your basic knowledge lah. This is the slip in single crystals. Does the slipping is important to understand? Slipping in general, it is important to understand, especially in the structure of FCC and BCC. But I will explain more in the next chapter, and you will see clearer how BCC and FCC plays a role in the materials. Okay. So slipping. Okay, so this is slip in single crystal, this is slip systems. Okay, so is there any more questions? So these four techniques of strengthening, you guys should memorize: solid solution, grain size, precipitation, and strain hardening. If everyone's okay, we can move on to the next chapter. This is very fast. I don't know, because I did not. Hey, are you guys okay? Okay ke? Okay. Alright. So is annealing include in strengthening? Okay, good question, Aziz. So annealing is included in the recovery and recrystallization of a material after it is quenched. So you can also say that annealing is a hardening process, but annealing is a section, or is a part of another process, which is quenching. After you quench, you anneal the process. Okay, so is that clear with everyone? Can we move on to phase transformation? So it's actually phase transformation, but there's also phase diagram and phase equilibriums that I will include here, and also the time temperature transformation diagram. So it's not just phase transformation lah. Okay, now we move on to phase transformation. So what is phase transformation? So phase transformation is why we do it is to obtain desired mechanical characteristics. The important factors of transformation is time and temperature. If you have a longer time, what does it makes? What difference does it makes? If you have a higher temperature, what difference does it makes? So it is a very detailed subject. It's a very detailed topic that we need to focus. So, and also how do we transform a material, or how do we transform the morphology of a material? So you guys might be asking, what is morphology? Morphology is the science of the form and structure. In this case, we are studying the microstructure. So transforming is basically changing the microstructure from one microstructure to another microstructure. Okay, so how do we do it? Is by using proper heat treatment. Heat treatment means you can introduce heat, and also you can also introduce heat, and also exert the heat. Wait, let me see. Introduce and remove heat. Okay, that is how heat treatment works. You can introduce and remove heat from a material. So what does removing and introducing heat does to a material? It develops new microstructure, altering the number and the character of the phases. So phases is an important keyword that we want to focus, because the topic is actually phase transformation. So obviously, so now we see what are the types of transformation. So if you want to change a certain microstructure, there are a lot of types of transformation. So first we go into the complicated diffusion. Okay, so change in number of phases and change in composition. So that is why it is called complicated, because the simple diffusion is there is no change in number of phases, no change in composition, such as solidification of pure metal. Like you have pure iron and you just heat it up and just cool it down. So that is a simple diffusion. Allotropic transformation, recrystallization, and grain growth. Okay, so what happens if we do not have diffusion? Do not have diffusion is a metastable phase of martensite. So each of these types of transformation is included in the phase transformation process. So you will see in this reaction, you have different types of diffusions. You have simple diffusion, you have complicated diffusion, and also diffusionless. Okay, now we see the example of the complicated diffusion, which is the eutectoid reaction. Okay, so what is eutectoid? Eutectoid, or the eutectoid point, is a point in the phase diagram indicating a solid is in equilibrium with two other solid phases, which is the martensite and also the ferrite plus cementite. Okay, so let us see here. So this is the most colorful phase diagram I can find, because all the phase diagrams in the internet is so boring, you know, it's like black and white. So this is like, oh, so colorful. So this is the eutectoid point. Okay, this is the border between austenite and also ferrite plus cementite. Okay, so you might be asking, why is the eutectoid here, not here or here or here? It's because that austenite meets in equilibrium with the ferrite. Okay, so why is it not here? Because it is not considered. Over here is pure iron. Here is iron and carbon. So this is not a eutectoid point. This is the eutectoid point. Okay. So now we will be talking about the eutectoid reaction. Okay. So first, there is the process of reaction. So if you have, how do you start this process? Is by starting at austenite. Okay. So we will be starting from austenite and we will work our way down to ferrite and cementite. Okay. So that is the process. So what is the steps, or what is the phases, or what is the, like, how the process of the reaction? Okay, so we start with nucleation. Nucleation is the formation of very small particles or nuclei of the new phase. Nuclei seeds acts as template for crystal growth. Favorable nucleation sites is imperfection sites such as the grain boundaries. Okay, so there are two types of nucleation. So, okay, you guys might be asking, what is nucleation? Nucleation is when you have a material. You have a material, kan? Then when that material cools down, liquid, or like the liquid phase of the material starts. There are certain points emerging from the middle of the liquid. So that points are called nuclei, nucleus. So there are two types of nucleation: homogeneous nucleation and also heterogeneous nucleation. So homogeneous nucleation, okay, let's see what does it mean. It means it forms uniformly throughout the parent phase. What does the parent phase means? It means whether it's in austenite or ferrite or cementite. Okay, so we'll touch this later. This is the single phases of iron carbon alloy: austenite, ferrite, cementite. Okay, so in austenite, some of the ferrites will be emerging. That is what we call the nucleus. So the difference between homogeneous and heterogeneous is that homogeneous is a slow process. It does not involve any nucleation site because the nucleus will emerge naturally. Like, it will emerge slowly because it is a slow process, and it occurs away from surface. Okay, what about heterogeneous? Heterogeneous involves nucleation site because it is not uniform. The heterogeneous nucleation forms at structural inhomogeneities in the liquid phase, which is the surfaces, the impurities, the grain boundary, and dislocation. Much easier and stable. So in the liquid phase, it is easier to form because it is much more stable and it has a nucleating surface. Okay, so you guys can see here the difference between homogeneous nucleation and heterogeneous nucleation. So physically we can see the size of the nucleus to be bigger for homogeneous, but the size for the heterogeneous to be smaller. This is because homogeneous nucleation takes a longer time because they want to form uniformly, and heterogeneous does not form uniformly, so it just emerges from the surfaces and it creates small nucleations. Okay, so the concentration of seed is also known as nucleus. Okay, let's put it here, aka the nuclei, or the points where transformation emerge. Okay, I think you guys can write that. Okay, the points where transformation emerge. Okay, so after you have nucleation, you have growth. Okay, so before that, we can also observe if how do we want to nucleate a material faster or slower. So the nucleation rate increases with the difference of time, delta T. The growth rate increases with T, temperature. So what does that mean? It means that if you decrease the temperature of a certain material faster, it will have much more nucleus. Okay, let's write here. Meaning to say, meaning to say, betul. So the faster you cool the material, more seeds emerge. Okay. So if you have more seeds to emerge, the distance between each seeds is smaller. Okay. Meaning to say, okay, let's give an example here. Seed in this grain, yes. So this is the liquid. So if the seeds are separated away from each other, they would grow. Okay, let's see. They would grow slowly until they meet each other. So the point where it meets, this is where we call the grain boundary. So this is like slow nucleation, or we can say as less nucleation and more growth, because the nucleus increases much more. Okay, in comparison to the nucleus, if they are situated closer to each other, so it wouldn't have much space to grow that much, but they would be much more closer to each other, introducing it introduce more grain boundaries. Okay, remember I said if you have more grain boundaries, the material would be stronger. Okay, so we want to have this type of transformation. This is the desirable transformation. Desirable. Okay, this is less desirable. Okay, so far so good. Okay, so that is nucleation. What about growth? Growth is defined as the increase of nuclei in size. So it reaches completion where the growth of the new phase particles proceed with equilibrium fraction is attained. It means it meets with other grain boundaries. Okay, so it will generate a grain boundary. So the time for process to complete depends on the temperature. So as we said here, the growth rate increases with time. So if you want to have a faster growth, you need to increase the temperature. Okay, increase the temperature Increase the temperature. Yes, increase the temperature. Increase the temperature. Okay. Okay, so what do we have here? Okay, so this is a transformation diagram. Okay, so during class, I didn't actually understand how does this diagram works. Like, why is there so many curves? I am not used to so many curves in one diagram. Okay, so now I will teach you how to read the diagram properly. Okay, so for example, you have three different processes or three different cooling. First, you cool it slowly. Okay, so this diagram is temperature against time. Why is it like this? Look. Time. So this is the initial and this is the T. So your experiment starts with here and then it will proceed horizontally. So if you decrease the temperature slowly, you will reach a point where the curve begins, or the perlite. Okay, so this is the first curve. And we have also the green curve, which is the 100% perlite. Okay, so this is what it actually means. The distance between the two curves is the time it takes to begin the transformation and ending the transformation. So as you can observe here, the temperature is kept constant. Ni subject material engineering materials, Lokman. Okay. So the temperature is kept constant. So we call this as an isothermal condition. Okay. So if we were to cool it down faster, it will go down and hit the curve at a lower point. So it will hit the curve here. And also if we cool it down faster, it will hit the curve lower. So what's the difference between each of the curves, or what's the point of having different cooling rates? Because in the end you have the same composition. Okay, so this is where this picture comes in. So as I said, if you have a fast there are three types of this is an example of three types of different cooling rates. Okay, so the first cooling rate is a slow cooling rate. So if the isothermal temperature that we set, the temperature that will be keeping constant is below the TE. TE is the eutectoid temperature. The eutectoid temperature for steel is 727 Celsius. So if it's just below the TE, the nucleation rate is low and the growth rate is high. Why is the growth rate high? Because it has a higher temperature. Why is the nucleation rate low? Because the difference in temperature is low. You see? This one. The difference in temperature high, the nucleation rate increases. But here, the difference in temperature is not high, so the nucleation rate is low. Okay, so we compare the first, second, and third curves. The first, second, and third methods, cooling rates. So the second cooling rate is moderately below TE. This is how we just compare. Just imagine you have another isothermal temperature which is much more lower than the eutectoid temperature. So the nucleation rate is medium and the growth rate is medium. So if you have a very drastic cooling, you would have a very big difference in temperature. Okay, let's write here. The delta T is small, but here the delta T is big. So when the delta T is small, the nucleation rate is lower, but the growth rate is higher. When the delta T is big, the nucleation rate is higher, but the growth rate is lower because it is operating at a lower temperature. T2, let's put here T3, also T1. Is everyone okay? Do you guys understand so far the transformation diagram? If you understand, you can put in the chat box. If you want me to explain again, I am open and I am okay. Faham? Lokman, lain-lain selain Lokman. Engineering material best though. Ini civil engineer memanglah boleh cakap macam ni. Mechanical engineer tak tahu tau. Malas. Tak nak. So anyone has any questions regarding the transformation diagram? Is everyone okay? Kenapa kamera aku sini? Okay. Alhamdulillah. Wah. Okay. Baru dapat baca. Yeah. So okay, together we learn this together. Okay, so now we enter the most important material in engineering. It is the iron carbon alloy. Okay, you guys put here the most important material in engineering. So FEC is iron carbon alloy. Okay, so let me explain on the phases. Okay, so there are two things that you guys need to understand properly. Wait, why my camera is like this? Okay, there are two things that you guys need to understand properly, which is the phase and the phase diagram. So this is pure iron. Pure iron has different we call phases. If the phases of water, the phases of water kan, you have solid, you have liquid, and you have gas. That is for like water kan. So if for steel, you have liquid, ferrite, austenite. So ferrite, austenite is called allotropes. So this is the base of, this is the primary phase. You guys can call it that. Also known as the primary or parent. The parent phase of iron is austenite, ferrite, and ferrite. So when we introduce carbon, only then the FEC carbon phase diagram is introduced. Okay, so you see here kan, the oh, ada Muhammad Daniel, Muhammad Nazri. Okay, let's go. How to use imagination. Nanti kita buat imagination. Nanti imagine sendiri-sendiri je tu. Aku ajar je. So after we learn this chapter together, insyaAllah everyone can imagine properly. Okay, Power tak sabar nak test esok. That is a very good question. Belajar simen bersama Dr. Mo. Tak nak dah belajar simen. Nanti belajar pasal batu. Tak bosan ni belajar pasal batu. Tak apa, kita teruskan. Where were we? We were here. Primary and parent phases. Okay, so this is pure iron. This is when iron combines with carbon. So this phase diagram ranges from 0 to 6.7 of carbon. Okay, why do we stop at 6.7 carbon? Because that's the maximum solubility of iron and carbon. Okay, so the 6.7% of ferrum of carbide is called cementite. Okay. So what is all this terminology? So let's explain together here. Okay, single phases is under the equilibrium condition. So there are austenite and ferrite. Austenite and ferrite is considered allotropes. Cementite is an alloy, because cementite is also known as iron carbide, Fe3C. Austenite is denoted as this is not sigma. Ingat apa? Sigma. Bukan sigma. Beta. I tak ingat. It's denoted as this apa? I tak ingat. Lambda rasa. It's denoted as lambda. Ferrite is denoted as alpha. So austenite, gamma. Thanks Bari. This is denoted as gamma. Okay. So austenite and ferrite is quite the same. Both of them are ductile. They are soft. Austenite is non-magnetic. Ferrite is magnetic. The main difference between what is that melody? Okay, jap. The main difference between austenite and ferrite is FCC and BCC. Okay, so remember I talked about the structure of FCC and BCC here. Okay, so it plays a big role in the different microstructures of ferrite and austenite. So that is the uniqueness of iron. It can change FCC to BCC. It is uncommon to find this sort of transformation in other metals. So austenite is FCC and ferrite is BCC. FCC is less dense than BCC. Okay, so let's see here. We have a diagram here. So this is the FCC. This is the BCC. Oh, sorry. The BCC is less dense than the FCC. As you can see, FCC here, you have a lot of atoms. You have like 1, 2, 3, 4, 5, 10. You have like 14 atoms in one unit cell. This is what we call a unit cell. But for BCC, you only have 1, 2, 3, 4, 9. You have only 9 atoms in one unit cell. So that is the difference between the body-centered BCC and FCC, and they also have different slip planes and slip direction. Okay. Okay, so now we talk about the cementite. Cementite is the carbide, which is the alloy. It contains 6.67% of carbon, and it is the hardest structure in the phase diagram. Okay, so now that is the single phases of FEC. Now we enter transformations under the non-equilibrium condition. So what is the difference between equilibrium conditions and non-equilibrium conditions? Basically, equilibrium conditions is very slow and uniform. Non-equilibrium is very rapid and non-uniform. So that is the main difference between equilibrium and non-equilibrium conditions. If you have equilibrium condition, it will just transform into these three phases. If you have a non-equilibrium condition, you have different types of phases. Okay, so remember tadi I said about the cooling rates, different cooling rates. So the different cooling rates here produces perlite. So what happens if we take it to the next level? Whoa, what does that mean? It means that we cool it much more drastically. If we cool, okay, we can see here. This is what we call the time temperature transformation diagram. So if we, this is the first diagram in the first page. This is the difference in T. Okay, delta T over dt is low. This one, delta T over dt is high. Nampak tak kita buat differentiation apa orang kata, the gradient, oh my god, the gradient of the curves are different. So what happens if we have different gradients of the curve? We would have different microstructure. So tadi kan kita yang awal tadi ni, this is to produce perlite. This, if we take it to the next level, we would be producing something else, which is called bainite and also martensite. Okay, so tadi actually I mentioned what's the difference of the end product of these two curves, one with the small difference in temperature and one with the big one. So the difference is, if you have a small difference in temperature, you would be having coarse perlite. If you have a bigger difference, oh my god, what is happening? Okay, we're back. Okay, if we have a bigger difference in temperature, we'll be having a fine perlite. Okay, this is a coarse perlite and this is also a fine perlite. Okay, that is the main difference between the curves, this curve and this curve. So what happens if we have much more rapid cooling? We will have different composition. Okay, so this kita sambung tadi, transformation under the non-equilibrium conditions. What does non-equilibrium means? It means it is an accelerated process. So there are three categories of cooling that we can divide, which is the slow cooling, moderate cooling, and also rapid quenching. So slow cooling and moderate cooling falls under 35 degrees Celsius per second. That will perlite and bainite. But for if you rapidly quench, you will have a higher delta T over delta T. This is delta T over delta. This one is higher. Delta T over delta T. This one is lower. Okay. So make sure you do that. So the Celsius per second for martensite, if it's above 35 Celsius per second, and the end product would have this is cementite and ferrite plus martensite. But if you have 140 Celsius per second, you would have completely martensite. Okay. So what is the difference between these three types of phases: perlite, bainite, and martensite. So perlite has alternating layers or lamellar layers. Bainite exists as needles or plates in the microstructure. This is the microstructure. Okay. So perlite has a fine plate-like shape. Bainite has like needles and also plate also. So the difference also between perlite and bainite is that perlite can have pro-eutectic phase, whereas bainite doesn't have pro-eutectoid phase. So what is a pro-eutectoid phase? Okay, so a pro-eutectoid happens when you have either hyper-eutectoid or hypo-eutectoid conditions. So let's say you have eutectoid. You have a eutectoid condition. So eutectoid will be starting in the middle here. Like we discussed, eutectoid is the 0.67% of carbon. So above that number, we would be having hyper-eutectoid. Okay, you need to remember that. But below that number is what we call hypo-eutectoid. So what's the difference between hyper-eutectoid and also hypo-eutectoid? Hyper-eutectoid has more carbide developing in between the grain boundaries. But for hypo-eutectoid, you would have more ferrite developing between the grain boundaries. Okay, you see here? So basically, this is the transformation of the different hyper-eutectoid and hypo-eutectoid. So the end product of hyper-eutectoid is perlite plus pro-eutectoid cementite. But for hypo-eutectoid, the end product would be perlite plus pro-eutectoid ferrite. Because you have much more cementite developing. This one you have much more ferrite developing. So you have a pro-eutectoid ferrite. This one you have a pro-eutectoid cementite. Okay, so that is the difference between hypo-eutectoid and hypo-eutectoid. Okay, so let's talk about martensite. So martensite is a super saturated phase because it is cooled rapidly, and it is also metastable. Metastable means it is not stable. You can also write here, not stable. Why is it not stable? Because it does not allow diffusion. So remember we said earlier the types of transformation. You have a simple diffusion. Oh my god, what do I do? You have simple diffusion, you have complicated diffusion, and also no diffusion. So this is a metastable phase, which is not stable phase. So this is the third type of the transformation. It does not allow diffusion. What it does is it transforms austenite to perlite under suppression. So what does that mean? It means that martensite, you be like cooling. Okay, we will talk about martensite over here. Okay, wait, is there anything else up here? Okay, we also have martensite here. Okay, martensite is when you skip you skip the phases. So because you rapidly cool the material, it would have no time to diffuse with other atoms. So what would you be having as the end product is a different microstructure. So this is the BCC from austenite. So if you have martensite, it will be rapidly cooling from austenite to martensite. You will be skipping. You will be skipping phases because you are rapidly cooling the material. So what happens is the carbon will be in the middle of the carbon atoms will not diffuse, but it will emerge in the middle of the space between the atoms. So the sites, this is what we call the sites. The sites might be occupied by carbon atoms. So the structure is called BCT. Okay. So BCC to BCT. So what's the difference between BCC and BCT? BCT has fewer slip planes. So that is why it makes it so strong. It's because it has fewer slip planes from BCC. BCC has more. BCT has fewer. That's right there. Fewer and more. Okay. So we can also see the physical properties. Difference between the physical properties of pearlite, bainite, and martensite is the strength and ductility. So the higher the strength, the less ductile it is. So it means that martensite is very brittle, but it is very strong. Okay. So martensite is stronger than pearlite. But pearlite is much more ductile than martensite. Okay, so that's like basic. You guys can tell by the arrows here. Okay, so let's talk about the stages of martensite. Okay, before we go here, is there any questions that you like to ask? Any question? Sejam baik. Pukul 30. No question ke? If we no question, we continue the time, temperature, and transformation diagram. So this diagram is the continuation of the diagram above here. No problem. Okay. So far so good. Okay. So this is from austenite to pearlite. You can see here, I put here slow cooling. Okay, so this is this one of the section of the transformation diagram. So this is the full transformation diagram. So pearlite tadi kat sini kan. Wait, let me. So pearlite tadi kat sini. So now we want to see how different cooling rates would have different outcomes. Okay, so how you guys want to read this diagram? Initially, I also don't know how to read, but now I will teach you how to read this diagram. So this is time. Okay, time. This you start here. This is T. So first you would start here, and then you cool down the material, and then you have an isothermal stage. Isothermal stage in order to keep the temperature at constant for you to get a desired composition, which is the pearlite. But if you want to have bainite, you should cool it faster, and then keeping the temperature constant at 300 degrees Celsius, macam tu. So okay, so different isothermal temperatures would have different composition. Okay, let's write it down. Temperature would be it means that we would have different composition or morphology. Okay. So if you keep the constant temperature at 650 degrees, it will be different if you keep the constant temperature at 300 degrees. That is the representation of this diagram. Honestly, once you get to know how to read this diagram, it will make sense lah. The first time I saw this diagram, I don't know why it curves so weirdly like that. I don't know why. Okay, now after we keep the material at a constant temperature, we would like cool it rapidly. Okay, cool it rapidly, and then you will get the final outcome here. If this is time, okay, so the length here is the time. Wait, you can't see it. Time. Okay, so if you keep the isothermal temperature longer, you would have a different percentage of that composition. If you would keep the time of that isothermal shorter, you would have a different percentage of the composition. So what does that mean? It means that if we wait more, you would have 100% of perlite. Now, if we wait more here, you will have 100% of bainite. Okay, but sometimes you desire something else, such as the 50% perlite or martensite. Okay, so you would stop here in the middle of the diagram, or the middle of the curves here. Okay, so that's basically it. So the points of the curves hitting the point of the process, hitting the curves, would mean different compositions. So this one you get 50% bainite, this one you get 50% perlite. In the end, you also get martensite. Why do you have martensite? Because you cool it rapidly, from here to here. This is a very big gap. Here, this is a very big delta T. Delta T here and also delta T here will generate martensite. Okay. So this is the stages of martensite. Okay. So you have the quenching process. Quenching process is cooling process, also known as cooling. You can cool it by water, you can cool it by oil. So quenching process is a high cooling rate. dt over dt is high. The factors can affect the cooling rate. Okay, so these are some of the factors Dr. Iswadi said about quenching. So if the material has a big size, too thick, it would have non-homogeneous cooling. If you have sharp corners, you have stress concentration, and you have high carbon content, it will affect the cooling curve. Okay, so non-homogeneous cooling. So that brings us to our next stage, which is the residual stress. The residual stress is the internal stress. Is the internal stress, oh my god, introduced. So the non-homogeneous cooling introduces tension and compression. The surface transforms faster than the core. The core transforms a bit late because the heat is not dissipated quickly from the surface compared to the surface. So let's write it here. Heat dissipates faster at the surface, but the heat from the core did not escape. Okay, so what does that mean? It means that the outer layer will receive pushing force from the core because it is expanding, because it is still hot. But the outer layer is in tension because it is already cooled down. So you have two different layers, the tension layer and the compression layer. This will introduce residual stress. So how do you want to eliminate this residual stress? It's by heating. So this heating process is also called annealing process. Heating for the second time. Okay. So annealing means it is recovery, recrystallization of the grain growth. This is to reduce the hardness so that we can improve the machinability. It can facilitate cold working, and we can obtain the required mechanical and physical properties of the materials. So that is all for FEC phase transformation. Okay, so is there any question? That was a very quick 1 jam je. Rasa I went very quick. Was I very quick? Do you guys need me to repeat anything? You guys need me to Thank you, doctor. Okay, sama-sama. I suggest you just go through and read the whole note, especially the first chapter. For the input, my brain is just not braining. Oh, okay. So you guys slow lah baca. Okay. So then I say, okay, thank you, Nabil. I'm sorry if I went too fast, but basically it depends on your capability of understanding it on your own time. I'm just here to tell you how the theory behind it all. 50% cost per light, 25% by night, 25% martensite. Okay. So if we would have 50% cost per light, you'll be going here. Okay. Here. And then here. This is let's say the curve is here kan. Okay. Wait. Let's just erase this. Okay, so this is how you do it. Here. And then straight here. And then we will go down. So you want to have 25% martensite and 25% by night. By night. This is by night here. So Okay. You will have two different time. Ni T1, also ni T2. Betul tak? I think it's like that lah. Then you go down here. Gotta pull back a bit on the binary, I guess. Pull back. Maksudnya apa? Dia memang kat situ. So memang cool down from here lah kan. Ke kat bawah ni. Okay, jap. Okay, I see what you mean. It's gonna be 50% per light and 50% by night. Okay. Maybe we can just put it like this. I think like that. The one you did previously. Oh yeah. Okay. Okay, I think it's like this. You will have T1, T2. This one would be T besar, T1 here, and also T2 here. Okay. So there's two steps if you want to achieve 50% cost per light, 25% by night, and 25% per button side. Okay, so I think that's how you do it. Curve would look like this. Okay, any other question? Okay. I think for this one you guys just apa ni? Apa ada bot ni? Apa? If you want to you guys can just read this through if you guys want to learn more. So I think that's it for tonight. So if there's any question, you guys can ask in the group. I would be glad to answer, and if this is not correct, I am also sorry. Okay, so I think that's all for tonight. Thank you for watching. You guys are great. You guys are wonderful staying till the end. Okay, I love you guys. Bye-bye. Cakap bye-bye. Hey, thanks. Thanks, Ajis. Thanks. You're welcome. Bye. Whoa.